Now we move to another thing called coding. What is coding? Coding basically means how do we send the signal when we want to send. For example, if you want to send a 1, we could send a long pulse, and when we want to send a 0, we could send a small pulse. That is one way to send zeros and ones. Another way is that whenever we want to send a 1, we send a +5, and whenever we want to send minus, we send a -5 voltage. When we want to send a 0, we send a -5 voltage. And there are other methods. Okay, so there are hundreds of methods of how we want to send ones and zeros. Right? Because I want to send a 1, but then it doesn't, I could decide that, well, for 1 I want to send 5 volt, or 10 volt, or 20 volt, that's up, up to the designer. Right? For 0, what I want to do, whether I want to change something in different in time or something in voltage or things like that. So there are so many variations possible. So that is called coding. And the smallest element that has to be measured, because if you are going to send +5 volt and -5 volt, the receiver has to figure out whether it is +5 volt or -5 volt. So the time that it gets to figure that out depends upon how long that signal stays at that value. So that time for which the signal stays at that value is called the signal element, and that is called the baud, actually. That is called the baud rate. So for example, if you were sending a big pulse and then a small pulse, it is the small pulse that really challenges the receiver, that figure it out in that small time whether it is minus or not. Right? So you take the time duration of that small pulse, and 1 upon that duration is called the baud rate. So if, let's say, you are going to send a pulse for 1 second and then a small negative thing for 0.1 second, then your baud rate would be what? So you have two elements here. One is 1 second and one is 0.1 second. What would be the baud rate? 10. Because you will take the smaller of the two, which is 0.1, and 1 upon 0.1 is 10. So you are sending 10 bauds, as we call it. 10, that baud rate is 10. Alright? Now the data rate is bits per second. So that is different, because for 1 bit, to send this 1, we decided that we are going to send 1 big pulse and then a small pulse. If you want to send the second bit, you have to send another big pulse and then a small pulse. So your bit rate is still, basically you are going to send 1 bit every 1.1 second. Right? So your bit rate is 1 upon 1.1. Understand? So there are many things we talked about now. We have talked about bit, we talked about baud, and we talked about hertz. And I just want to make sure that you understood. What is hertz? Cycles per second. Right? So if you take any signal, you can convert that into a sine waves, or a combination of sine waves, and then the primary frequency that you use for that sine wave would be generally called the hertz for that signal. Okay? Then you can calculate the baud rate. If it is a digital signal, then it will have some stable values. If it is not a digital signal, if it is an analog signal, it will be just going all over. So there is not one time in which you can say, well, it will stay at -5 volt for so long. So then baud rate doesn't apply. But if you have a digital signal, then it will be constant for some time. So you take that smallest time, and 1 upon that would be baud rate. Good. And the bit rate is how many bits you are sending. 1 bit may consist of many elements. 1 bit may require, in some cases, I wouldn't do it, but basically you may say, well, I will send for 1 second positive 5 volt, then for 0.1 second I will send minus, and then I will send for another half second +1. So you could have any coding you want, right? So you decide the coding you want, that this is your +1 bit, 1, and then you could have something else for -1 or 0, right? So you need a binary signal. So that coding will determine what is the bit rate. There are coding in which 1 bit consists of many elements, and there are coding in which 1 element consists of many bits. So for example, you could have a coding in which you could say that whenever I say +5 volt, that means 1, 1, 2 bits. When I have +2.5 volt, that means 0, 1, 2 bits, right? When I have 0 volt, that means 2 0 0 0. So you take 2 bits at a time and then you decide what voltage you want to send. So each baud consists of 2 bits, right? Or it could each bit could consist of 2 bars or 5 bars or 3 bars, right? So there are both possibilities. You could have more bits than bars. You could have more bars than bits. It depends upon the coding. And you will soon start actually getting the hertz as well. So for example, this signal, if I told you that each of these horizontal parts is 1 second, what is the hertz rate of the signal? Half cycle per second. Why? Because this is 1 second and this is 1 second, the whole cycle, you have to take the whole cycle. You start from 0 and then when you come back to 0, it takes 2 seconds. Each cycle is 2 seconds, right? So this is half cycle per second. On the other hand, if I would have said that each of these is 1 microsecond, then what is the hertz of this? 2 microseconds. See, the cycle is this. You have to understand. You can start at any point, but you have to come back to the same point. So for example, generally you start from the middle, you go down, and then you come back to the middle. That much is 1 cycle. Okay? A sine wave is like this, complete cycle, right? It starts from a 0 and goes back to 0. So a complete sine cycle would be starting from here, going back to there. So this is the total time. The total time is how much now? If each element is 1 microsecond, how much is the total time? 2 microseconds. So 1 upon 2 microsecond is how much? Is 500 kilohertz. Right? Because 1 upon 1 microsecond is a million. Half of a million. Half of a million is 500 kilohertz. Okay? Alright, so now you know the difference between bits, bars, and hertz. Given any signal, you should be able to calculate what is the bit rate, what is the baud rate, and what is the hertz. Alright, let's see some coding things. One coding is that we would send when we want to send a 0, we will send a positive signal, sine wave with a positive, with a phase of 0, and when we want to send a 1, we will send a positive, with a sine wave with the same amplitude but with a phase of 180 degree apart. Okay, remember each sine wave has 3 things. It has amplitude, phase, and frequency. Right? So we selected a coding, and people have tried all kinds of things. One person selected the coding where 0 is represented by a sine wave and 1 is represented by the same sine wave but 180 degree phase. So we just have to measure the phase of the signal. And so if we were to draw on a diagram where we measure we plot the phase as an angle, so we will plot 0 as this point. 0 means there is an amplitude, but the phase is 0, and this is phase 90 degrees, and this is phase 180 degrees, and this is phase 270 degrees, and so on and so forth. So 180 degrees phase means 1, 0 phase means 0. So this is one way of indicating, and this coding is, by the way, called differential PSK. PSK stands for phase shift keying. We are going to just change the phase. And differential means basically if it's same phase as before, then it is 0, and if it is opposite phase, then it is 1. So that is the differential PSK. Now, there is something called QPSK, quadrature PSK, in which we use 4 phases. If the phase is 45 degree, then it is 1 1. If it is 135 degrees, it is 1 0. If it is 270 degrees, it is 0 0. If it is no, not 270. See, this is 45, 135. 135 plus 90 is 215. 215 plus 90 is 305. So 305 is 0 1. Okay, everybody can see the angle, right? So what we are doing is we are plotting. So whenever the signal comes, all we try to do is, we already know the amplitude is going to be same because all 4 points have the same amplitude. Amplitude is represented by the length and the phase is represented by the angle. So if we see that the signal that is coming to us has a phase of 45 degrees, that means the other side is sending us what number? 1, 1. Alright? And if they were sending an angle, if the phase was 135 degrees, that means they are sending 1, 0. So now we can, using the same kind of things, we are able to do 4 positions, actually 4 bits. We can do actually 2 bits at a time. See, with this one will allow only 1 bit. So by the time we figure out what the phase is, let's say it takes 1 second to find the phase. Alright, with this coding, how many bits we can send? If it takes 1 second to find the phase, it will be 1 bit per second because it will take 1 second to find the phase, whether it is 0 or 1. With this coding, if it takes 1 second to find the phase, how many bits can we send? 2 bits per second. Right? And both of these have the same frequency, same hertz, so the hertz is not even a question here, right? And but the question is how much. And now, but obviously you need a system which can do 45-degree resolution in 1 second, which is difficult than to do 180-degree resolution. Here the resolution is just, we have to know whether it is 180 degree or 0, which is much easier than to find out whether it is 45, 135, And we can keep increasing this. We could do 2 points, 4 points, and we could do 16 points. With 16 points, we would like to figure out whether the amplitude is little or big or medium, and whether the angle is this much or that much or that much, 45 degrees or 22 degrees or something like that, right? So this is called QAM 16. This coding is called QAM 16. In the beginning, when we started, this was a tough thing to do. Then people figured out how to do QAM 4. Then they figured out how to do QAM 16. Today, in the wireless world, we use QAM 256. Can you guess how does QAM 256 look like on this graph? 256, just have to take the square root of 256 and figure out how many rows and columns it will have. 16 by 16. Right? So by the way, 256 is still beyond the reach in the sense that it will cost you a lot of money. If you buy a cheap equipment, it might be 64. So right now we are somewhere between 4 by 4, 64 is 6 by 6, right? Sorry, not 8 by 8. 8 by 8 is 64, right? And 256, so 8 by 8 is 64, and 256 is 16 by 16. So somewhere there in between. So 256 is still, but next year when you come, or 2 years from now, 256 would be very easy, and then we are struggling with the next one, which would be, 1024. Right, something like that, because you just keep. So this is where what is happening is now all of these signals have the same frequency, but we are able to get so many bits out of that same frequency, a lot more bits, right? Because what is happening now? There is one more thing which I didn't point out here, that this is a 4 by 4 matrix. But what we have done is to get 4 by 4 matrix is that we have put 4 bits in each combination. So each of these combinations is 4 bits. So this would be 0, 0, 0, 0, this might be 0, 0, 0, 1, this might be 0, 0, 0, 1, 0, and so on and so forth. There are 16 combinations. Where this is only, so this is, each dot is 4 bits. Right? So this is 4 bits per baud. For each time we figure out what dot is, we have already told you 4 bits. Now for 64, you have 8 by 8. Okay, so we are putting more and more bits, and then now to be able to decode this stuff, you really have to have a receiver that can distinguish these amplitudes. See, the thing is, this amplitude and this amplitude are different, right? Amplitude is the line which goes from the dot to the origin, right? The length of the line. So these amplitudes, we have to be able to distinguish a small from the medium and from the large one. This one is large. And in 256, there are even more gradation, right? And then you have to be able to distinguish the phase. In this case, it is 22 degrees phase you have to distinguish. Here it is 45, 90 degree phase you have to distinguish. Here 180 degree. So this is more and more difficult, and therefore the circuit is more and more expensive. Okay? So now what I have taught you, I will be using this QAM word very often. So I will say QAM 16, QAM 64, QAM 256. Now you understand what QAM is. QAM is quadrature, amplitude, and phase modulation. Alright? And so this is the amplitude and phase modulation. We are changing the amplitude and we are changing the phase. Okay? And so this is the coding that is used in DSL. When you get a DSL on the wire in your home, and remember previously when the DSL was first given, they gave you only 1 megabit. Now they're giving you 2 megabit. Then they're giving you now 6 megabit. How are they doing it? It's the same wire, right? But what they're changing is, what are they changing? The coding. And so previously they were not able to do QAM 64 on the wire, right? But this year they're able to do, so they're giving you more. Next year they're able to do QAM, 128, QAM 256, and so on and so forth. They keep going up, so they can get more and more bits on the same wire for the same hertz. Same thing is happening on the wireless. Previously, when we designed the wireless signal, we couldn't get 2 megabits. After that, we were able to get, on Wi-Fi. Then we were able to get 10 megabits. Then we were able to get 56 megabits. And now this year, you are able to get 200 megabits almost. So the number of bits per second is keep going up, while the spectrum has not changed, and the key is the coding. So next thing is the antenna. The transmitter. What antenna does is, it gets this electrical signal somehow and transmits it out as electromagnetic waves in the air. And how this electromagnetic waves goes is, there are people whose sole job in life is to design the antennas, and they get PhDs and lots of PhDs in antenna design, and there has a lot been work done in the last few years. So if you make a dumb antenna, a very simple straight wire, then what will happen is power will go in all directions equally, right? So what this is showing is, if you went to this direction, how much power will you find at this distance, right? And you say 1 milliwatt. Then you go to in this direction and same distance, how much power will you find is 1 milliwatt. So if you draw the 1 milliwatt line, that will be a circle. Obviously, if you measure the power closer, it might be 2 milliwatt. Closer, right? By some distance will be 1 milliwatt. If you go farther away, it will be half milliwatt. So if you draw these lines which are equal power line, then you can see how the power is being transmitted. If the power is being transmitted equally in all directions, that is called omnidirectional antenna. Right? But generally you don't want power to go in all the directions equally, because if I'm trying to talk to him, there's no point in my sending the power in that direction. Right? So people became smarter and they started making directional antennas. And directional antennas look like this. What is this? This is the power spectrum of the directional antenna. So there is a lot more power in this direction and very little in the backward direction. So whichever direction you want to send, a lot more power goes in that direction and very little goes in the other direction. Alright? And so what then we do is, then we measure at some distance d, what is the power. If it was omnidirectional, then obviously the power would be 4 pi d square. So basically what it is that generally if you didn't do anything, the power will go in a sphere, right? And the sphere has an, if the diameter of, if d is the diameter, so then you can figure out what is the area of the sphere. The power will be equally divided in that whole area, right? So pi r square, for example, is the periphery of a circle. 4 by 3 pi r square, I think, is the area of the sphere, right? So given that, you can calculate what is the area of the sphere, and since this antenna is so good that we get a lot more than what would come out, so we measure the gain of the antenna by this method. So gain of the antenna is PR, the received power, equal to transmitted power times the gain of the transmitting antenna, and GR, which is the gain of the receiving antenna, times lambda, which is the wavelength, divided by 4 pi d square. All right, and now we are not going to go into this whole formula derivation, but the idea is that if you had a dumb antenna, then they will not provide you any gain. So both of these numbers will be 1, and your received antenna will be strictly proportional to the transmitted antenna power times the lambda upon 4 pi d whole square. So as you go more and more, the d square is with that r square we were talking about. The area keeps going up and going up, and so your power keeps going down and down. The power density actually, and which is going down, and also the frequency has an effect. The wavelength, lambda is the wavelength, by the way, not frequency. So lambda is the wavelength. So the wavelength also has an effect, and therefore it is lambda square as well as 4 pi d square. So lambda upon 4 pi d. If you get anything more than that, then it is either the transmitting antenna or the receiving antenna, which is smarter, right? And so you could have a receiving antenna which is directional and it only receives in this direction. You could have transmitting antenna which is directional, which only transmits in this direction, or you could have an omnidirectional transmitter but a directional receiver, right? So any combination is possible, and depending upon how much gain you get from the transmitter, how much gain you get from the receiver, you can calculate what is the received power. So when you go and buy an antenna in a computer store, have you seen what kind of antenna they are selling? Like they say something about the antenna, how they specify an antenna? Anybody remembers anything? Yeah? Yeah, so they tell you, like, can you remember any antenna which is being sold as to what they sell you for? I mean, what dB they say? Yeah, actually not minus. They will say 7 dB or 10 dB, right? I have seen many 7 dB antennas. So what that is that the GT is 7 dB. If you use that antenna compared to some other antenna, you will get 7 dB more power in the direction you want. Or actually there is another thing too. Even if you don't want directional, many antennas will, it's like resistance. Many antennas will just, you give them some power, most of it they will consume themselves, they will become hotter, they will convert that into heat, and very little will go into the air. Power can go either way, right? It can become heat or it can become electromagnetic waves. So a normal antenna will produce some amount of electromagnetic waves, but this 7 dB antenna will produce 7 dB more. All right. So depending on how much you want to pay, you can buy a 10 dB antenna. If you want a 10 dB, that will be much more expensive than 7 dB. If you went and bought a 20 dB antenna because you want to go 2 miles, yeah, you can buy a 20 dB antenna, but that will cost you a lot more. But one thing you see from here, so there are several things on this slide. First thing you understand is directionality, right? Second thing you understand is that there are both transmitter and the receiver gains, right? Third thing is that the lambda makes a difference, the wavelength makes a difference. If you send a signal which has wavelength twice as much, you can get 4 times as much power at the same distance. Second thing is that the power goes down by the square of the distance. Why does it go down by the square of the distance? Can anybody explain why it goes down by the square of the distance? The area that we are measuring the power over goes up by the square of the distance. So if you are measuring something at 1 centimeter, you get 1 centimeter square, right? When you're measuring at 2 centimeters, it is that much big area, right? 4 times bigger area. However, in practice, it is not d square. In practice, it is d raised to 4. So that we'll talk about later on, but for now, it is d square. Okay? Now, there are other ways of losing power. And so when somebody is sending something, let's say this car is sending a signal, a wireless signal, some of it will strike a building and will be reflected, just like light, right? It will be reflected and go there, It will be reflected there and go there. So this is called reflection. Every building acts like a mirror. Every surface acts like a mirror for the wireless signal. Okay? If I transmit something from here, it will hit that wall, it will be reflected. Right? Some of it will strike something small object and it will be scattered everywhere. So, I mean, you can think about the light, hitting something, some diamond or something, little diamond, and then it will be scattered everywhere. Right? So, similarly, the electromagnetic waves, the wireless, can be scattered, which is different from reflection. Reflection actually is still stays in the straight line, and it still power is all transmitted, whereas scattering is going all over. The word name scattering simply says that, the power is distributed in all directions. And some of it can be diffracted. So diffraction of light, and if you send a light, some of it will be reflected and some of it will go into the glass but go at a different angle, and we call it diffraction. Right? So same thing happens to the signal here. Some of them will be diffracted. So all of these things happen: reflection, diffraction, scattering for the electromagnetic waves, because electromagnetic waves are a form of light. Right? Other way around. Light is an electromagnetic wave, and so are the wireless signal. All right. So we already talked about all of this: reflection, diffraction, scattering. When you have a reflection, the signal may change its phase. It may change. Obviously, it changes its angle, but it also may change the phase. Or it may also change the amplitude. Diffraction, same thing happens, and then scattering. Depending upon how big is the object and compared to the wavelength, if it is, suppose you are sending a signal which has a wavelength of 1 micrometer and the object itself is 1 micrometer, it will scatter. As opposed to if the object is very big, then it will think about reflecting. Right? But the object is very small and you send a big wavelength wave to it, it will be scattered. And we use another term called LOS, line of sight. Line of sight simply means a straight line. So what is the difference between scattering and reflection? So let's say we have 1 micrometer object, but I send a light to it. Now light is a very small wavelength. It has nanometer wavelength. That will be reflected. On the other hand, if I send some TV signal, which and particularly I send maybe radio signal which is very small frequency, so very long wavelength, they will be diffracted. Now, multipath. Another thing that happens with the wireless signal is that because things are reflected, you get many copies of the same signal. If I send something, in fact right now you are getting many copies of my voice. My voice is not an electromagnetic wave, but since the voice goes, it behaves almost the same way. It goes, it hits the wall, it is reflected. It hits that wall, it is reflected. So you get many copies of the same sound. However, since the walls are so close, the sounds are coming within few microseconds and your ear is able to not really see the difference. So it just hears only one. If there was a mountain, big mountain far away, then my voice will go to this mountain, my voice will go to that mountain, you will be able to hear the echo. So those echoes are called multipath. Is that when we send a signal, we send one signal, generally we expect that we will get one copy, but you don't. What happens is you get one reflection, another reflection, another reflection, so you send one but you might get 4. So this is your first pulse. Then your second pulse you send and that you get 4 copies of that. However, if these things are very close, you are sending too many bits per second. This is your first bit, this is your second bit. If these bits are, you are sending too many bits, then your first bit will get merged into the second bit. When you hear the second bit, you are hearing some of the first bit and the second bit. Right? That is called the interference. Inter-symbol interference. That is called the inter-symbol interference. You send the first symbol, and by the way, we call these things symbol, not bits, because remember, each symbol could be 6 bits, or each symbol could be 4 bits. We saw that QAM thing. So each dot was what? Each dot was a symbol, right? And each symbol could be any number of bits, right? So if you send this symbol and then you send that symbol, you got 4 copies. So if there is enough multipath, actually it depends upon, first of all, we measure the delay spread. So this symbol could be heard even after this time, so the spread is very large. Since the spread is large, we cannot send too many bits. We cannot send too many symbols, because if you send too many symbols, they will just merge each other into each other and you will get confused. You will get a lot more errors. So the delay spread is the time between the first and the last version of the signal. So in this case, the delay spread will be from here to there. Right? And why do we have this delay spread? Because signal is going to be reflected from here, which is, first of all, some copy will be reflected from here and quickly come here. Something will go all the way there and then come back, so that will be delayed more. Something is going far away and then coming back, and will be delayed even more. So you get multiple copies of different amplitude and different times. And so when you, so basically that is the delay spread we measure. Fading is the change in the amplitude, or phase or delay, whatever we are measuring. And the multipath may add constructively or destructively. So that's another thing. So you may get 2 copies of the signal, but it is quite possible that the 2 copies are out of phase, means they are 180-degree phase. So one comes, gives you plus 5 volt, and the other one comes and gives you minus 5 volt. So you get a 0 signal. Even though I sent something, but the 2 copies cancelled out each other. Or it is quite possible that they add together. So I sent you 1 5 volt, and you get 1 5 volt, another 5 volt, and you might get 10 volt or something like that. So 2 copies. So the thing is, so the multipath can be constructive or destructive, and that randomness, that can cause randomness depending on what it is called fast fading. That is called fading and fast fading. That change in the amplitude because of this multiple copies is called fast fading. So anyway, the summary of this slide is that whenever you send something, depending upon the environment, what is surrounding you, you will get multiple copies of the symbol, and we have to really find out how long is the maximum delay spread before we can decide how fast we can speak. Right? How many bits, how many symbols we can send. Because if the delay can be long, like for example, we talk about the mountain, in that mountainous area, you cannot be speaking very fast because you keep giving your lecture and people are going to get 2 copies of the lecture and they're going to be confused, trying to decipher those echo from the original thing. Right? But here in a small room, there is no echo, so I can send a lot more bits. Now let's move the speaker. So if suppose a train is making a sound, horn, train, now when the train is coming towards you or the train is going away from you, can you distinguish? Without looking at the train. Train is coming from behind you, you are not even looking at the train, but you suddenly hear a sound, or even a car for example. Can you tell whether the car is going towards you or away from you?
Yes.
Yes, and that is because this Doppler spread, Doppler shift. What happens is that when the car is coming towards you, even though the signal that horn is making has some frequency, let's say it has 10 cycles per second, which is not. Actually, it might have 10, maybe 1,000 cycles per second. That is what the sound sounds like, 1,000 cycles per second, 1,000 hertz. However, because the car is coming towards you, you probably are getting 1,100 cycles per second because the car is coming towards you. On the other hand, if the car is going away from you, you are only getting 900 cycles per second. Okay? And so you can figure out, oh, the signal frequency is going up, so the car is coming towards me. Your ears can figure that out. The signal frequency is going down. Obviously, actually, amplitude is also going down, by the way. When the car is coming towards you, the amplitude is going up, right? And when the car is going away from you, the amplitude, but the frequency also changes. So that amplitude and frequency change. So that change in frequency is called the Doppler shift. And it can be very easily calculated how much is the Doppler shift. Doppler shift is exactly equal to the velocity of the object divided by the wavelength. If this was going at 10 kilometers per second, you just take that 10 kilometers per second and then divide by the wavelength of the signal it is sending, and you will know how many cycles per second you're getting more or less. Okay? So if I gave you an object velocity moving, and the reason this is important is because we are going to design wireless networks for the cars, right? And so a network that will work in this room where you are not moving will not work when you are moving in a car, because then there is an additional thing to worry about, the frequency change. For example, WiMAX is designed for only cars going up to 60 kilometers per hour. If you want faster cars, then you have to design another thing, another network. All right? So the Doppler, and the reason is because Doppler shift. So how do we calculate that? We take the velocity and divide by the wavelength. Here is an example. We have a 2.4 gigahertz signal, and therefore from that we can calculate the wavelength. Wavelength times frequency is equal to what? Not 1. Is equal to speed of light. 300 meters per microsecond, right? So that is the number here. 3 times 10 raised to 8. That is the speed of light divided by 2.4 gigahertz gives you the wavelength. 0.125 meters, which is 12.5 centimeters. Now, if you are going at 120 kilometers per hour, you divide that into seconds because you want to have it in the same unit, meters per second. You divide that meters per second and then divide by whatever, then you get the frequency differential, 267 hertz. So that is how much the frequency will change. Instead of 2.4 gigahertz, you will see 2.4 gigahertz minus or plus 267 hertz. Not much, but you have to worry about that. All right, the key formula is right here. Velocity divided by the wavelength. So you should be able to calculate the wavelength, and velocity is generally given to you. And you have to just make sure that you don't use, if you are using hours there, the frequency difference generally is in seconds, so everything has to be in seconds. To calculate 120 kilometers per hour, we have to convert that somehow into per second. So we divide it by 3600, and then kilometers, so kilo, so we multiply with 1000. So that gives you meters per second. Now we can divide by meters and get hertz. Right? All right. Now we talk about channel capacity. So channel capacity is basically, there is a Nyquist theorem which says that if you have a binary signal, if you have two levels, just two levels, okay, plus 5 volt or minus 5 volt or plus 5 volt and 0 volt, as long as you have two levels, and if you use only B cycles per second, then you cannot get the data rate more than 2B. So if I said to you that, well, I want to use coding theory, I want to design a coding which has two levels, but you have a 100 hertz signal, then you cannot get more than 200 bits per second. There is no way. Okay, as long as only two levels. If you want to get more than that, then you need more levels. And that's what we do in QAM. QAM is not two level. QAM has multiple levels. As we go more and more QAM, we have more and more levels. Right? So here's a multi-level signal you haven't seen so far, but here's a multi-level signal. For example, in this signal, what we have done is we have taken 2 bits and then made 4 amplitudes. So 0, 0 is here, 0, 1 is here, 1, 0 is here, 1, 1 is here. So depending upon what is the value I want to send, we will send that level. So now this has actually 4 levels, and for m levels, the Nyquist theorem says that you cannot get more than 2 times the bandwidth times the log 2 of m. Okay, so m is 4, log base 2 of 4 is how much? 2. So you cannot get more than 4 times the bandwidth. And so on. Now I could give you a signal which is, by the way, if I were to ask you how many cycles per second, now let's say each element is 1 second. Suppose I told you that each element here is 1 second. There are 2 elements here, by the way, right? What is the cycle length here? What is the hertz rate for this signal? So you have to start from some point and come back to exactly the same point, full cycle. So you start from here, you go from here all the way up to here, go up to there and go up here, and then come down here. Just before the horizontal line you would draw, that would be the end of the cycle. So this whole cycle is 1, 2, 3, 4, 5, 6, 7, 8, not 16. It is 8. Okay? And so wherever you start from 0, and then you come back to the 0 from the same direction, because you start from 0, you came to here 0, but you haven't completed the cycle, that is only half of the cycle, and then you are coming back here. So that would be one cycle, and this whole thing is actually 2 cycles here. Alright, the next theorem we have to teach you is Shannon's theorem, and Shannon, basically a professor at MIT, he came up with the idea that what happens if you have noise? And he said that if your signal to noise ratio is S upon N, signal to noise ratio is S upon N, then you cannot get any more than B times log base 2 upon log base 2 of 1 plus S upon N. So if the signal to noise ratio is 30 dB, first of all, this is not in dB, this is a linear graph. So we have to take anti-log of this to calculate the real signal to noise ratio. So what we do is we say 10 times log base 10 of S upon N is 30. That is what 30 dB is, right? So you do the anti-log and you come up that the signal to noise ratio is 1000. If the signal to noise ratio is 1000, then it would be 30 dB. So then you do the capacity, would be whatever the bandwidth is, 3100 Hertz, and 1 plus 1000, you take that, and so you cannot get more than this amount. And this is by the way log base 2. So you have to keep your bases straight. We do log base 10 when we are doing the dBs. We do log base 2 when we are doing the Nyquist theorem or the Shannon's theorem. Right? When you use Nyquist and when you use Shannon's, Nyquist has to do with how many levels you have, and Shannon has to do with how much noise you have. Alright, so if I gave you the noise, you worry about Shannon. If I told you the levels, then you worry about Nyquist. If I gave you both, you worry about both. Then there is Hamming. Hamming taught us how to measure the errors, how to quantify the errors. So if I sent you 0111011 and you received 110001 instead, so how many bits are in error? How many bits are wrong in those two? First, 1 bit is wrong, 3rd bit is wrong, and then the last, this 5th bit is wrong, right? 3 bits are in error, right? So the Hamming distance is 3. So basically, what we do is, we do exclusive OR of what was sent and what was received, and then we count how many ones are there in that exclusive OR. So we sent this, we received that, we do the exclusive OR, bitwise exclusive OR, there is no carry here, right? And then we count the 3 ones. Those are the 3 bits in error, right? So our goal is when we send a signal and we receive a signal, the Hamming distance would be how much? 0. Right? And if it is not 0, then we are concerned we have some bits in error, and the more Hamming distance there is, the more problem there is, right? And so when we design the error correction code, we put extra bits so that when we send, the symbols that we are sending, they are far away, so that when they get to you, you don't confuse one for the other. For example, if I want to send you 0, 0, instead of sending 0, 0, I will send you 4 zeros. When I want to send you 0, 1, I will send you 0, 0, 1, 1, 1, 1. Actually 5 zeros here, so I'm going to send you that. When I send you 1, 0, I want to send you that, and then 1, 1. So basically what I've done is, instead of sending 2 bits, I'm going to send you 5 bits. And the codes that I've selected here are such that they're far apart, as far apart as I could make them. So the distance between, what is the distance between this and that? Can anybody tell me what is the Hamming distance between these two numbers? 3. So if 1 bit goes into error, you are still safe. You can figure it out, you can correct the error. If 2 bits get into error, you are still safe. But if 3 bits get into error, you are not safe, because if these 3 bits became 0, I had sent you 0, 1, but you are thinking it is 0, 0. Right? So the Hamming distance tells you how many bits can go into error and still not be, a problem. So when we design, now this is another coding, as people get confused. So this is another part of coding theory. One part of coding theory people they work, codecs actually we should call them, those people work on how to send waves. And another part of people, another set of people, totally different set of people, they work on how to design these codes. Instead of 0, 0, we are going to send 0, 0, 0, 1, 1. And there are other possibilities, by the way, right? Because if you take 5 bits, you have 32 combinations, we have to select only 4 out of those 32 combinations, just 4 combinations out of 32 combinations. Which 4 should we select? We should select the 4 combinations which are farthest apart from each other. Alright? So we did that. So in this case, basically when you receive something, you can figure out whether you can correct it or not. So this code, 3 bits will not be detected. This code will not detect 3 bits, but it will detect 2 bits and 1 bit and so on and so forth. It might, by the way, detect 5 bits in error, but you won't be able to correct it. So each code has a certain power in terms of how many bits it can correct, how many bits it can detect. So the turbo code idea came up very recently, actually in 1993, when somebody said that if you want to do coding better, you should have 2 codes. You should use 2 codes, not 1 code. And what you do, you take some input and then you send it to one coder, which is called upper coder, and whatever extra bits come out, that bits, and whatever bits you had, combine it with the extra bits coming from this coder. Plus you take the same input and interleave. Interleave means you just change the bits around and then send it to another coder, and then whatever comes out combined with that. So combination of all these 3 things you send out, then you have very high bit rate. Then basically you can get very close to the Shannon limit. So the Shannon limit says that if you have a signal to noise ratio of S upon N, this is the maximum you can get. Most people were not able to get that close. Given 3100 Hertz media, most people were not able to send 30,000 bits per second on a signal to noise ratio of 1000. Even though this is a theoretical limit, but people couldn't find in practice do that, right? But with turbo code, you come very close. You come within 0.5 dB limit of that. So we gave you, I think it was 30 dB, so you get as close to as, if the noise was 29.5 dB, what Shannon says, you can get that in 30 dB scenario with turbo coding. So turbo coding is basically using 2 codes such that before sending to the second coder, you change the order of the bits somehow, randomize the bits and then send it. And randomize means you know exactly how you randomize it, because the receiver has to de-randomize it exactly in the same way. So when we say randomize it, it's not really truly random. It's with some kind of formula we randomize it, change it, so that the other guy uses the same formula to reach unrandomize it. We call it pseudo-random. Pseudo-random means that it looks random, but it is not really random. Right? So we randomize the bits, and then we send to the second coder, and then we combine all these 3 things, and then we send that output to the other side, and then the other side will. So for example, in this coding, what we have done is actually, if you notice, the middle 2 bits are same as these 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. Right? And we have added 3 extra bits. So those are the bits that we are talking about, the parity bits. Those are the parity bits. Those are the extra bits. Right? So we take the original signal, we take the parity bits from the one coder, we take the parity bits from the second coder, and we combine all that and we send it. We can come very close to the Shannon limit. And now we are going to move on to a totally different topic, and that is another kind of coding, is that what we call frequency hopping. So military had this problem that if they use any frequency, the enemy knows what frequency it is, and they can just jam it. They can start sending noise on that frequency, right? So they said what we will do is we will change our frequency every few seconds, few microseconds or few milliseconds. So I'm transmitting to you at this frequency. This is the frequency for this time, and a 50 millisecond later I will switch to the other frequency, and then 50 milliseconds I will switch to the other frequency. Now you and me both have already agreed upon a randomization formula. So you know this pseudo-random number generator, and I have the same pseudo-random number generator. We both have the same generator. So I generate a number from that, and I know that I have to send the red frequency, and you know that you will receive red frequency. 50 milliseconds later, we generate a new number, and we will go to that, you will go to that. And so we are all in sync, but the other guy, third guy, who doesn't know anything about our random number generator, will not be able to catch with us. Right? And so that provides protection against jamming. All right? And so that is called frequency hopping. Frequency hopping is when we change the frequency every few milliseconds using a pseudo number generator. And believe it or not, you are doing it every day. When you use a Bluetooth device, you are using frequency hopping. When you are using Wi-Fi, in some modes of Wi-Fi, we use frequency hopping. All right? So one, and why do we do it? Not because we want to avoid the jamming, but that is how we avoid colliding. So you are speaking, I am speaking at the same time. If you won't want to use the same time, same media, then it's better off that we both frequency hop. So we might collide once in a while, but most often we will not collide. Right? So when you have 10 computers in a single room, how do they not collide? By frequency hopping. Right. So what they do is, that's a very good point, is that if my clock starts in the middle of somebody else's clock, I would get half at this frequency and half at other frequency, and I'll be very confused. But what happens is, before we start communicating, we send a signal which basically synchronizes the clock. So we send a training signal which tells you exactly where my bits begin. So that signal is well known, 0, 1, 1, 0 or something, some well known sequence, and then you have to, as long as you, until you get that, exactly that sequence 1, 0, 1, 0, you know that you are not synchronized. Now here is the last thing to say about frequency hopping, is that it was not really invented by military, it was invented by an actress, Hedy Lamarr. And Hedy Lamarr was practicing with piano keys. Piano keys are a similar thing. They have, each key produces a different frequency. And she was practicing with some kind of thing as to how we can mix up the frequencies and things like that. And she came up with this idea, she patented it, and then actually during her time herself, she figured out that this can be used for communication, and I think she probably made some money out of this. So anyway, so now this is used quite often. And this is, military loved it because of the jamming thing, but now we all love it because of media sharing. All right, so frequency hopping. Now the net effect of frequency hopping is that you might be actually sending a signal generally which is at one frequency, has a lot of power at that frequency. Noise generally is much lower power, but it is kind of at all frequencies. So if you were to x-axis was frequency, y-axis was power, in the frequency domain, a normal signal looks like this. But with frequency hopping, we are sending some power at this frequency, some power at that frequency, some power at that frequency, some power at that frequency. So if you take an average over a long period, the signal is spread all over. Right? It might even be less than the noise. However, at any one particular instant, it is like this. At any particular instant, you see the power is at one particular frequency. But when you take over a long period of time, power is spread. So that is why we call it frequency hopping spread spectrum. What we have done is we have spread the power all over the spectrum. All right. When you go to buy a phone, cordless phone, they come up with the spread spectrum. Remember? There is another method of spreading a spectrum, and that is called direct sequence spread spectrum. And that one is actually much simpler. In that case, what we do is we take one bit, and instead of one bit, we send many, many bits. So for 0, I will send 0, 1, 0, 0, 1, 0, 1, 0, 1. And for 1, we will send just the opposite of that. So each one selects a code. We call this code, and this is your bit, and this is what we call, not bits, we call it, so for the time being, let's just call it code bits. So this is your data bit, and this is your code bit. So for each data bit, you are sending 10 code bits. All right. This also has a similar effect that if there are 100 people in the room, each one could select their own code. Right? And so when they send a 1 and I send a 1 and you send a 1, everybody sends a 1, the receiver can figure out which one they want to listen to because they know which code to listen to. Alright? So this is called direct sequence spread spectrum. This also has the same effect because now instead of your frequency being this, which was maybe 2 bits per second, you have now 20 bits per second. So the signal spreads all over. So this is also a spread spectrum, but this is called direct sequence because you are using so many bits. So actually the military might use 10,000 bits for each bit. Instead of sending 1 data bit, they will send 10,000 code bits. Actually, I remember the word. It's called chips. So they will send 10,000 chips. Right? That's very secure because by the time you figure out which combination this guy is using, they would have gone home. So the idea is that generally in our thing we use 10 or 100 chips per bit, but military uses a lot more chips per bit because they want security. Coding, this is called code, by the way, CDMA, code division multiple access, because everybody selects a code, and if the codes are correctly selected, then one person's code does not apply with another person's code. It's like language. If you go to your room and there are 100 people, somebody is speaking in Chinese, somebody is speaking in English, somebody is speaking in Hindi, you know what? If you are a Chinese and somebody is speaking in English, it will not bother you at all because they are not interfering with your signal at all. Right? And if somebody is speaking Chinese, it will not interfere with the English people. But if there are 2 people speaking English, then their ear is kind of hurting because they are trying to, reject, and it's difficult to reject that signal. So code division multiplexing is like languages. All right, here is a summary of 4 things that I want to tell you today. First of all, now you know the difference between hertz and bits, and they are related by the Nyquist and the Shannon theorem. So if I gave you some hertz and asked you how many bits can you do, you have to use one of those 2 theorems. When do you use the Nyquist theorem? When I have given you number of, Nyquist theorem relates to what? Number of levels. And the Shannon's theorem relates to noise ratio. And then we have to worry about reflections, diffractions, scattering, multipath, fading, Doppler shift. There are a lot of things that can happen. Then we talked about frequency hopping and direct sequence as the 2 methods of CDMA. And then we talk about turbo codes, right? And then if you wanted to read about many of these topics, I have put the URLs here from places where you can go and read. Electromagnetic spectrum, you can go. Most of these are, by the way, from Wikipedia. And I found that Wikipedia generally has more information than I want to give it to you, actually. So when you go to Wikipedia, you find a lot more. Say, for example, you go to phase shift keying, you find a lot more than what I have given you here. But that is good and that is bad is that, good is that, at least you have something to read more. And bad is that you probably will end up reading a lot more than, we need for this course, but that's fine. So just be selective. That is a good point to go. And so we have all these reading material. So you will know more about each topic that we are talking about.